So I wanted to show off an idea I had for a programming language. I call it DCL, which stands for Domain Checked Language. The idea is that all variables have a domain restraint on the types. And with this, the compiler can enforce correctness. Languages like C++ and C have undefined behavior because they want speed. For example, not checking an if every time you do array access, but this language doesn't have undefined behavior. It's compiler enforced that undefined behavior is not possible. There's a few other things in this language. One of them is I call reference semantics. You can see in this out here. It's kind of an extended version of what you can do in C#. There's no manual memory management. You do initialize variables on the heap, but you never free them. It's determined that when it is freed. I'm pretty sure this is almost exactly what Rust does. It's explicit in how you use the variables instead of inferred though. So in my opinion, I think it's a better one. This language also uses extensions to add functions, which I think Rust does too. I've never actually programmed in Rust. I just think I independently came to the same conclusions. I've heard that many people say writing in Rust feels like fighting the compiler. But I want to make that struggle feel like a walk in the park. Anyway, let's talk about the basics of this language first. In most languages, an add operation is the most basic. You can just add two variables and it won't complain. But in this language, that's not the case. The compiler has to know that this add will not result in an overflow. It won't let it happen. And you can see in this last one, this last function, that the requirements are explicitly marked here. So you can see the x can be anything, but y is limited by the value of x. And this filter will make sure that this add will never result in an overflow. And of course, the result is returned as the sum of the domains of x and y. Now, it's a bit too much to expect the programmer to write this every single time. So here you can just mark a function as auto, and it'll figure that out for you. It'll be a compiler error if you don't. So functions will also report all their side effects. This is a more simple one, but I have some more interesting thing here. You can see everything here is fine. There's no error because the domains show that x and y do result in a possible add operation. But you can see there's a warning here. And the warning is that the result is less than 9, yes, but it's actually less than that. It'll never be 9 since x and y are always less than 5. The maximum value of the result is actually 8. And so that's a compiler warning just because it'll, if you reduce it, then it can do more. You don't have to have as many if statements. But this isn't the best way to do it. There's another warning here. We're telling the compiler that the result here is only less than 9. But less than 9 relative to what? We can actually do the same thing we did down here in the full sum and say the domain is the sum. That means if the compiler gets anything that's even less than these values or has a greater than 0, it can tell that this value, it can get the actual true domain by just adding the two values. All this is intended to make invalid calls impossible. All checks are pushed up to the user input, so runtime performance should be fast. Compilation times though, especially with some of the other features of this language, I'll have to see when I get more of it working. Anyway, let's go to the next example. This is an implementation of a stack backed by a list. I haven't fully finalized the language, of course. I do have some of the parsing working, but imagine that the list works fine. As you can see, there's generics. Generics can accept any value, and I do mean any value, but here it's restricted to types. The stack reports the list count as a property, but you can see its domain is restricted equal to the count itself. There's a reason for this, and we'll go over that, but let's look at the interesting part here, the functions. You can see that all functions have a when clause. These are compile time constraints that are actually necessary to call the list operations. They happen to be shared by the stack because it's backed by the list. So for a push, we have to make sure the count isn't already at its maximum value. The maximum value is of course limited to the 32-bit unsigned integer limit, because what would happen if you were to add another one? It wouldn't even know about it. What happens after the push? Well, we can see that its side effect is reported by the then clause. It increases the count by 1. We know this is obviously correct, so why don't we tell the compiler that's what it does? Pop also has a when and then clause. Peek only has a when, and that's because it has no side effects, it only returns the value. I am considering moving all the type domains from the function parameters like you saw in the test to the when clause. It does the same thing, and it would unify the style, it would simplify it, but we'll find out later. So what happens when we tell the compiler what these operations do? Well, we can have something like this. Say we create a stack. Of course, when it's created, it reports its domain, and the counts domain is 0, just as the constructor said it was. Then we immediately pop. In any other language, this is a runtime error. You could never catch this. Not here. The compiler checks the domain of count to see if this operation is possible. Of course, 0 is not greater than 0, which means this is a compiler error. As you can see, in the next example, doing it in the correct order works fine. If we look at foo here, the stack is being passed in with no domain constraint. Count can be any value between 0 and the integer limit. So what happens if we try to push? Compiler error. Pop works though. We know that whatever count the stack had after the push, it's x plus 1. And x plus 1 is always greater than 0. Bar correctly adds a check constraint to the stack. This means that it should have enough space for its one push operation. It then calls pop, and we know it's valid. So let's look at bar 2. It has a slightly more restrictive constraint. It calls push and then bar, which means it needs to have 2 open spots, which this enforces. And that's fine. Now let's see the last example. Here, we forgot to pop what we pushed. And now that means that the side effect is reported by the function. If the function were not auto and didn't report the side effect, it would have been a compiler error. But this one isn't auto, and it does. If it were auto, then this would then propagate upward, and we would then find a compiler error, and then we could say, where is this extra push coming from? And we can follow the chain of side effects to find the correct place where the error occurred. This is the most interesting example. This is because I was using Dear IamGUI for UI, and I kept having begin and end issues. Sometimes you just forget to put it. You compile, and then it gives you an error. Here you can see another basic feature of the language. Any code can run at compile time. Now this is just a basic sample. You can look at how it's written in the constraints for a little bit. Pause if you want to better look. How this works is very likely to change. This might not be how it works. You might not need this constant value. Constant values probably won't be modified within the function itself. But in the end, the result will be the same. The compiler will enforce the order of calls and how many there are. If I scroll up here, you see begin window, end window. And this would be an error because we forgot to call end window, because render expects the count of the stack to be 0, which means everything was popped. Here would also be an error. We called begin group, and then we used end list. But the top of the stack isn't a group, it's a list. And so it would report this. So I'm still working on this language. I only have basic parsing. I'm still working on a lot of things, but this was an interesting idea that I thought about, like I said, after I was programming IamGUI, and I realized that this language could actually fix a massive class of bugs, and one that is usually very hard to find the errors with.